In this lecture, we will study volts ampere characteristics of PN junction diode. X-axis represents voltage across the diode and Y-axis represents current through the diode. In this lecture, we will draw volts ampere characteristics for both forward and reverse bias condition. And if you remember the forward bias condition, we connect positive terminal of the battery to the P side and negative terminal of the battery to the N side. So first I will make the circuit. This is the symbol of diode. This is P side, this is N side, and we will connect P side to the positive potential and we will connect N side to the negative potential, and voltage across the diode is equal to VD and current through the diode is equal to ID. Now from diode current relation, ID is equal to IS, where IS is reverse saturation current. In bracket we have E raised to power VD divided by eta VT. This is eta ideality factor minus 1. This is the equation of diode current, and if we consider the condition in which VD is equal to 0, it means voltage across the diode is equal to 0. We can also call it no applied bias. This is the no bias condition, and if you see this plot, you will find this is VD equals to 0 and we have to find the diode current at this point. I will use this equation, ID equals to IS e raised to power 0, because VD is equal to 0, so we have e raised to power 0 minus 1. Now e raised to power 0 is 1, so we have ID equals to IS 1 minus 1. 1 minus 1 is equal to 0, so ID is equal to 0. So this is what we have when the voltage across the diode is equal to 0. The diode current is also equal to 0, and thus we have diode current equal to 0 when VD is equal to 0. Now we will increase VD in positive direction, not in negative direction, and we can say that diode is forward biased, and on increasing VD, width of depletion layer decreases on increasing VD, and also barrier potential decreases, but still diode current is equal to 0 because the barrier potential is strong enough to prevent electrons crossing the junction. But if you go on increasing the VD, if you go on increasing the forward bias potential, VB reduces further, and there is small current through the diode because some electrons will cross the junction and there will be current through the diode. So there is small current through the diode, and when VD is equal to VB, it means the forward bias potential is equal to the barrier potential. There is flood of electrons crossing the junction and we have rapid increase in current, as you can see here. This is the plot of germanium and this is the plot for silicon, and in case of germanium, barrier potential is 0.3 volts, and in case of silicon, barrier potential is 0.7 volts. So if we consider the case of germanium, if VD is equal to 0.3 volts, it means VD is equal to barrier potential. There is flood of electrons crossing the junction and current will increase rapidly, and if you increase the VD further, the current will increase exponentially. So there is generous flow of current through the diode if VD is greater than or equal to barrier potential. And in case of silicon, if VD is greater than 0.7 volts or even equal to 0.7 volts, we have generous flow of current through the diode. So this is all for VI characteristics in case of forward bias condition. Now we will move to reverse bias condition, and in case of reverse bias condition, positive terminal of battery is connected to the N side and negative terminal of the battery is connected to the P side. So first I will make the circuit. This is the symbol of diode. We will connect P side to the negative potential and we will connect N side to the positive potential, and the voltage across the diode is VD, and we have to find current through the diode. So we will use this equation, ID is equal to IS in bracket e raised to power Vd eta Vt minus 1. I will use this, and in this case we have Vd negative, or we can say that Vd is less than 0. So this is what we have in case of reverse bias condition. This is for reverse bias condition, and if we make Vd negative, then let's see what we have. ID equal to IS in bracket we have e raised to power Vd eta Vt minus 1, and now this Vd is negative, so e raised to power Vd eta Vt is less than 1, and this is when Vd is negative. So we can neglect this term, and we will have ID equals to IS minus 1, or we can write ID is equal to minus IS. So the direction of current in case of reverse bias condition is opposite to this direction, and we have only one current in case of reverse bias condition, and that is the reverse saturation current, and the direction will be like this. This is IS, reverse saturation current. Reverse saturation current is also called as leakage current. This is also called as leakage current, and this is the only current in case of reverse bias condition. Now we will try to analyze the plot in case of reverse bias condition. This is for forward bias condition, and there is one thing in case of forward bias condition, the diode current ID, it is equal to I majority current due to majority charge carriers minus I saturation, the saturation current. And when depletion layer decreases, when width of depletion layer decreases, the majority current due to majority charge carriers increases, and because of this diode current also increases. And in this case we only have reverse saturation current. In reverse bias condition, we only have one current, that is the reverse saturation current, because I majority is equal to 0. So the diode current is nearly equal to IS because I majority is equal to 0, and we already know the reverse saturation current only depends on the minority charge carriers, and the cause of minority charge carrier is temperature. So the number of minority charge carriers is fixed. Let me write this down. Number of minority charge carriers is fixed, and because of this we have a very small current in the beginning. If you go on increasing the temperature, the current will not change, and this current is IS, reverse saturation current. It is very small current in order of microamperes. You can see in order of microamperes, and this is very small because it only depends on the minority charge carriers, and the number of minority charge carriers is very small. That's why they are called as minority charge carriers, because they are small in numbers as compared to majority charge carriers. And if you go on increasing the voltage, if you go on increasing the reverse bias potential to a higher value, you will find that there is a sudden rise in current. This graph is for germanium and this graph is for silicon, and there is sudden rise in current. This voltage is known as breakdown voltage. Let me write this down. The voltage here and this voltage here is called as breakdown voltage. Breakdown voltage or Zener voltage. Zener voltage. It is called as breakdown voltage because at this voltage breakdown of diode occurs. Now we have to understand breakdown. What is breakdown? And this is the most important point of this lecture, and it is very interesting and very simple. On increasing reverse bias voltage to a very high value, the electrons will acquire a very high kinetic energy, and they will break the covalent bond and become free. These free electrons will again collide with the electrons and free them, and the process will continue like a chain reaction. So what is happening here? When you go on increasing the reverse bias potential, the electrons will gain the kinetic energy. They will have the kinetic energy which is very high, and they will break the covalent bond and collide with other electrons. Now we have 2 electrons. These 2 electrons will go and collide with other 2 electrons. Now we have 4 electrons. These 4 electrons will free 4 more electrons. Now we have 8 electrons. So there is a process like a chain reaction, and we have to be very careful with this condition. So this is the VI characteristics in case of reverse bias condition, and this is VI characteristics for a normal diode, for a simple diode. We also have other type of diodes like Zener Diode, in which doping is very high, and Zener Diode is very good if you want to operate in reverse bias condition. In Zener Diode, breakdown is achieved earlier because it is highly doped. In the coming presentations, we will discuss Zener Diode, which is very important topic. We will also solve numerical problems on it. And it is very important to know the voltage at which diode is operated in reverse bias condition, because this will destroy the diode, and we must know the reverse bias operating conditions for a diode. If a normal diode is subjected to the large reverse bias potential, it cannot withstand the high power being dissipated. So we use Zener Diode for this purpose. And now there is one term, peak inverse voltage. Let me write this down. Peak inverse voltage, and this is the last point in this lecture. What is peak inverse voltage? It is the maximum reverse bias voltage that can be applied across the diode before entering to the Zener or breakdown region. So this is the maximum value of reverse bias voltage that we can apply across the diode before it enters to the breakdown or Zener region. This is the breakdown or Zener region. Breakdown or Zener region, and the peak inverse voltage is the maximum reverse bias voltage that we can apply across the diode before it enters to the Zener or breakdown region. I will advise you to write this down, because sometimes this type of questions comes in exam, and at that point you cannot recall what is PIV or peak inverse voltage. So this is all for this lecture. See you in the next one.